So, the program that we have seen here, the timer 1 is acting as an event counter. So, this is pin 3.5. So, that is T1 pin. So, there I am feeding the pulses that are coming, and then this set B, as we have said that set B 3.5 will make this port 3.5 as input port by making it high. Then for our display purpose, we can say that I can have 8 LEDs connected on this port P2's lines. Okay, so we have seen that we are outputting this count of TL1 through A register onto this P2. So, we can do that here. So, we can connect a number of LEDs here. So, you can connect something like this, maybe put a resistor, then we put one LED here, put an LED here. So, this way for each of them we can have a current limiting resistance followed by some LED. Okay. So, that way for every point we can connect one. So, 8 such LEDs can be connected. So, it will have a nice display of the pattern of number of pulses that are received in this T1 bit. And since we cannot display a number more than 8 bit wide. Okay. So, in port P2 it has got only 8 lines. So, we have got 8 LEDs. So, that is fine. So, we can just reload this counter with 0 after there is an overflow to FF. So, next we will look into another example. So, like this. So, we assume that a 1 hertz frequency pulse is connected to pin 3.4, and we want to write a program to display counter 0 on an LCD. So, this whatever be the counter 0 value, we want to put it on the LCD. So, initial value of TH0 we set it as -60, and from that point onward. So, it will be continuing. So, in the first round it starts with 0 and counts 256 events, and since on reset TL0 is 0. So, what we have to do it, we do not want that. So, we want to reload we want to load this TH with 0 with -60 at the beginning of the program. So, let us have a look at the program. So, first this LCD setup part, so initializing LCD. So, this ACALL LCD setup. So, that is not a part of our this program. So, we assume that there is an LCD setup routine. So, which will be doing this LCD setup part. So, some control words are to be set to LCD and all that. So, assuming that it is already done by this LCD setup routine. So, we initialize this counter 0 in mode 2. So, again the same thing. So, these lower order 4 bits. So, they will tell you like the mode setting, and so it is a counter now, and it is mode 2. So, TH0 is initialized to -60 and set B P3.4. So, this will make this T0 as input, just like in the previous example we are using set B P3.5. So, here we have to use set B P3.4 to set T0 as input. Then set B TR0, it will start the timer, it will start the counter and move A comma TL0. So, after every 60 seconds, so we have loaded T0 with -60. So, after 60 seconds it will be after every 60 such events. So, there will be the timer will overflow. Okay. So, move A comma TL0. So, then we convert this ACALL convert. So, it will convert in some registers R2, R3, R4. So, again this routine is not a part of our discussion, because this is some display routines that uses this register R2, R3, R4 to maybe to hold this hour, minute and second part of the display. So, that is not shown here. And then we check this TF0, the TF0 is overflowing, then we go to back. So, that means we have one loop is over. So, TL0 value will be again. So, if it is not bit, so it is not yet over, then this the TL0 value will again be going to A, and then this converter will convert the value into this hour, minute, second display, and this display routine will be called. And when this bit is set, then now this TR0 has to be stopped, the timer has to be stopped, and this overflow flag has to be reset. So, that is done, and it is again going to start that timer. So, this way we can have a program for this purpose. Next we consider the situation where gate is equal to 1 in the TMOD register. So, whatever we have discussed so far, their gate was equal to 0. So, nothing so externally there was no control. So, everything was controlled by the internal TR bit. So, we have used set B TR0 and set B TR1 for timer 0 and 1. Now, if gate is equal to 1, we can use the hardware to control the start and stop of the timers as well. So, that is many times that is useful, and they are done by this INT 0 and INT 1 pins. Okay. So, INT 0 is pin number 12 of port 3 is bit number 2, and pin number INT 1 is pin number 13 of port 3 is bit number 3. So, they can control the timer operation. So, if this gate bit is set to 1, then for timer 0, whenever this INT 0 is activated, then only the timer will operate, and if it is deactivated, then the timer will stop. So, that way we can have control both externally and internally for these timers. So, for turning on the timer for the software side, for internal turn on, so we have to use this instruction set B TR0. So, that remains. Apart from that, we can have this external gate equal to 1. So, if gate equal to 1, it will count up if INT 0 input is high and TR0 is equal to 1. So, if these two conditions are satisfied, then only the up counting will take place for gate equal to 1, and for gate equal to 0, it will be only the software control. So, only TR0 will be equal to 1 will be sufficient. So, this we have seen. So, there are many special function registers with respect to timers. So, this TCON register's address is 88 hex, it is bit addressable, and as you see that the last digit is 8. So, it is that's why it is bit addressable. So, whenever you have got this last digit as 8 or 0, the register is bit addressable in case of 8051. Then TMOD register, it is the mode control. So, its address is 89 and it is not bit addressable. Then TL0, TL1, TH0, TH1. So, these are all these timer values, low byte and high byte, okay, and they are not bit addressable. Then we have got this T2CON. So, T2CON is for 8052, and we have got some low byte captures. So, these are some timer 2's modes, some special modes are there. So, for that purpose these registers are used. Next, we will look into the interrupts. So, in case of 8085, we have seen interrupts, and then we have seen that there are different types of interrupts that are there in 8085. RST interrupts, then INTR, trap and things like that. So, in case of 8051, we have got two interrupt lines, INT 0 and INT 1 as the external interrupts, plus there are some other interrupts that they are actually internal interrupts. So, we will look into them. So, this diagram is very generic. So, if the interrupt occurs at this point, so it will be jumping over to the ISR, the corresponding interrupt service routine. It will finish off this ISR, and this return return from interrupt. So, this instruction, so it will take it back to the instruction from where it was interrupted. So, it was interrupted at this point. So, the processor jumps after finishing this move B #10 #20 instruction. So, after completing this instruction, the processor will come back and start this multiply AB this instruction. So, in case of 8051, there are 5 sources of interrupts. Okay. So, they are called timer 0, timer 0 overflow, timer 1 overflow, then external interrupt 0, external interrupt 1 and serial port interrupt. So, these are the various interrupts that we have. So, timer 0, timer 1, we have seen that TF0 and TF1 bits. So, as I said that you can either poll it in a program, or you can have a interrupt generated when the overflow has occurred. So, there are some enhanced version of 8051 that has got 22 different sources. So, the advanced version of 8051 that has got more timers, programmable counter arrays, ADCs and more external interrupts, then serial interrupts. So, they are there. So, but the basic 8051 has got only 5 interrupts. So, we will try to understand how these 5 interrupts will operate. So, if the interrupt event occurs and interrupt flag for that event is enabled and interrupts are enabled, then the interrupt will be recognized. So, first of all the interrupt should be enabled, as we have seen for 8085 also all the interrupts should be enabled, and we can have masking of interrupts. So, here also the same thing, that interrupt flag for that event must be enabled for the masking purpose. So, the interrupt is not masked off and the interrupt has really occurred in the world. Okay. So, if all these things happen, then only an interrupt is considered to have occurred and it will be taken care of by the processor. How is it taken care of? So, first the current program counter value is pushed onto stack, and before that you can write down step number 0, which is basically finishing the current instruction. So, we can write another step as step number 0 here. So, which says that finish current instruction, finish current instruction, the instruction that it was executing, and then only it will be going into the interrupt service routine. So, after that, after finishing the current instruction, so it will be save the program counter value into the stack, and the program execution will continue at the interrupt vector address for that interrupt. So, in case of 8051 all the interrupts are vectored interrupts. Okay. So, there is nothing like non-vectored interrupt like INTR in 8085 we had. Here all the interrupts are vectored interrupts. So, their addresses are fixed. So, execution will start at a fixed address, and then after some time when this interrupt service routine is over, then this program counter this ret-i instruction is encountered, and then the program counter is popped out from the stack, and the program execution will resume from the point where it was left off. So, that is the thing. So, this is the standard interrupt operation flow. So, that is true for other processors also. The only thing is that in case of 8051 the interrupts are all vectored interrupts. Next we look into the interrupt priorities, like what if two interrupt sources interrupt at the same time. In case of 8085, so there is a priority setting, and we have seen that the trap has got the highest priority, and then that is non maskable interrupt, then 7.5, 6.5, 5.5. So, they have got the priorities in that order. So, in case of 8051 also, so we have got the concept of priority. The interrupt with the highest priority will get service first, and all interrupts have a default priority order. So, priority can also be set to high or low. So, that can also be done. So, these are the interrupt priorities. So, there are some special function registers that are useful for these interrupts. The first special purpose register that we will look into is called interrupt enable. So, this interrupt enable, so it has got 7 bits 8 bits, out of that this bit number 6 is not meaningful. So, it is not documented, like for what is the purpose of this bit number 6. So, that is not documented. So, we so for as far as the user is concerned, so we cannot do anything with this particular bit. So, this first bit or bit number 7 is the enable interrupt. So, this is the enabling this is for enabling all the interrupts in the system. So, it is a global interrupt enable, and it must be set to 1 for any interrupt to be enabled. So, this EA must be set to be equal to 1 for this enable, and if EA is 0, then all the interrupts in the system they are disabled. Then this bit number 5 is the ET2. So, this is the timer interrupt. So, we have got this timer interrupt 2. Okay. Then this we have got this. So, that is true for timer 2. So, timer 2 8051 we do not have timer 2. So, that is in 8052 you will have, but this bit is there in 8051 also. Then we have got ES0. So, this is the serial interrupt or serial communication interrupt. So, we have so for serial communication we have got both byte receive and byte send, but both of them are controlled by this ES0 by a single interrupt. Okay. So, there is both receive and transmit, they are they generate the same interrupt ES0. Then we have got ET1. So, ET1 is for timer 1 for, so this is then EX1 for external interrupt 1, then we have got ET0 for timer 0 and EX0 for external interrupt 0, and there is also a reset value. So, reset value for this interrupt enable register is all 0. So, you see that initially all the interrupts are disabled, and this interrupt enabled register is A8 hex, the address is A8 hex. So, for any reasonable system design that allows the interrupts to be occurring in the outside world, so we should set this EA bit to 1. So, this may be one important step in the whole operation of the system, that the EA bit should be turned on, otherwise none of the interrupts will be sensed by the processor. So, that this TCON register that we have seen previously, it comes once more when we are going into this interrupt discussion. So, we have seen this higher order nibble, this these 4 bits. So, they are dedicated for timers, timer 1 and timer 0, they are overflow flag and the run flag. So, those 2 bits, but this lower order 4 bits. So, they are actually IE1, IT1, IE0 and IT0. So, IE1, so this is set by the CPU when high to low transition detected on external interrupt 1. So, this will be, so when there is a high to low transition on this interrupt 1, then this IE1 bit will be set, and accordingly this IE0 bit will be set if there is a high to low transition detected by the processor on the interrupt on the INT0 line. So, there are 2 interrupt pins, INT0 and INT1, and whenever it sees a high to low transition on those lines, these pins are these bits are set to their set to proper values, they are set to 1. And then we have got IT1. So, IT1 is the interrupt 1 type control. So, if it is set or cleared by software to specify the falling edge or low level triggered. So, if it is so you can control this set this IT1 bit. So, if you set this IT1 bit to 1, then it will be a falling edge triggered falling edge triggered sensing. So, when the interrupt line goes from low high to low, it will be taken to be interrupting the system, and if it is 0, then when the line INT1 line is low, it will be taken as interrupt for the processor. So, we have to be careful in setting these interrupt types. So, depending upon the device that we are connecting to this to the system. So, we may like to have these interrupts of type this edge triggered or level triggered, but both are low, both. So, edge triggering also high to low edge, and this level triggering is also this low level triggered. And similarly, we have got this IE0 and IT0 bits for the INT0 interrupt. If you look into the priorities, so we have got, so this is the default priority. So, INT0 has the highest priority, followed by TF0 timer, that is timer 0, followed by interrupt 1, followed by timer 1, then this RI plus TI. So, this is receive interrupt and transmit interrupt. So, these are for serial communication. So, they are by a single interrupt. So, that is why we can write it as RI plus TI, as if one interrupt is generated. So, this is the default priority. So, this immediately tells you that if a number of interrupts occur simultaneously, then the processor will first respond to INT0, and if INT0 is not there, it will respond to TF0, TF0 is not there, it will respond to INT1. So, it will go like that. But unlike 8085, so here you can alter the priority setting. So, you can say like this, that we have got this PT2. So, this is one register which is called IP register. So, interrupt priority register. The first 2 bits do not have any functionality. Then this PT2 is the priority of timer 2 interrupt. So, PS is the priority of timer serial port interrupt. Then PT1 is the priority of timer 1 interrupt. So, then the PX1 is the priority of external interrupt 1. PT0 is the priority of timer interrupt 0, like that. Now, if you set one bit to any of those bits to 1, that interrupt will assume the highest priority. For example, if you look into this command, so move IP, this instruction move IP comma 00000100B, the binary pattern. So, so this PX1, this bit is 1 and rest of the bits are 0. So, in that case INT1 will assume the highest priority. So, this order will now change and it will be something like this. So, once you do this thing, this setting, so my INT1 will have the highest priority, INT1 followed by INT0, then TF0, then INT1, sorry, then INT1 is already done. So, the TF0, then this TF1 and then this RI plus TI. So, the order will change. Okay. So, order will change, so that we can have this thing, it will be representing the new order. Okay. So, you can change the priorities, and so that interrupt will assume the highest priority and rest of them will follow the previous order. So, naturally it raises the question that can we have this situation, can we have more than one bit set to 1. So, if you do it like this, then these two interrupts, so 1 1, so I am looking for, so this interrupt and this interrupt, they are set to 1 and rest are all 0. So, that means that these two interrupts, so they will acquire priorities higher than the remaining ones. So, your interrupt INT1, sorry, this timer 1 and this external interrupt 1, so they will assume the highest priority followed by others, and within them, within these two, the priority will be decided by the default priority order. So, if you consult this relation, then you see that this INT was between INT1 and timer 1. So, INT1 has got the higher priority. So, as a result, if you set it like this, then INT1 will have the highest priority, then it will be followed by this TF1. So, like this. So, this relationship will come. So, INT1 will have the highest priority followed by TF1, and then that will be followed by rest of the interrupts in the same order. So, so INT0, TF0, then RI plus TI. So, they are the remaining interrupts. So, they will be following in the previous order. Only thing is that these two interrupts, they will have priorities higher than others. So, naturally you can understand that you cannot set this interrupt priorities arbitrarily. So, there are some values, some of the interrupt combinations are feasible, but you cannot set all of them simultaneously, but still, but that is a good option, like we can change the default interrupt priorities, and this is particularly true because in a system when you are designing the microcontroller based some embedded application. So, it may so happen that you need to take interrupt from different sources and at different times of program or different phases of program. So, you may require the priorities to be different. Though, so instead of connecting the changing the hardware connection, so you can just change this interrupt pattern, the interrupt priority pattern, so that so that this changing priority will be taken care of. So, that is the interrupt priority register. Next, we look into the interrupt vectors. Okay. So, interrupt vectors. So, as I said that in case of 8051, all interrupts are vectored interrupts. Okay. So, 8051, so 8085 it had got only a few vectored interrupt and INTR was non-vectored. So, here in case of 8051, this vectored interrupt, their addresses are fixed, like this reset. So, it will take you to the address 0000. So, this address is fixed. Then this INT 0, external interrupt 0. So, this address is 0003, timer 0 is 000B. So, you see, if you look into these two locations, okay, 3 and B. So, you have got only 8 memory locations in between. So, if you are writing the interrupt service routine for external interrupt 0. So, if you find that these 8 bytes are sufficient, then for holding your interrupt, then it is fine. If it is not, you have to take care of. So, that is, so you have to use some sort of jump instructions and all that, as we see, as we have seen it 8085 as well. Now, so these are the interrupt vector location. So, so this serial interrupt, this has the highest address 0023 hex. and this timer 2 overflow is that is for 8052. So, that is 002B. So, that way we can have different interrupt addresses, the vector addresses. So, this is fixed by the designers. So, to avoid overlapping of interrupt service routines, so it is common to put jump instruction like here, say we are putting say at origin say 00. So, we are putting this LJMP say EX7I SR. So, this is some interrupt service routine, external interrupt some service routine, and this is the main program is at 100. So, it from this main program starts. So, now I can so on reset. So, on reset this interrupt will be coming to the system will be coming to this 000B address, and there it is seeing this instruction. So, at this point I can have the code for doing the reset operation. So, that way it is the reset operation will take place. So, this is an example where we have got this pin 3.3, that is INT1 connected to a pulse generator, and we will write a program in which the falling edge of the pulse will send a high bit to P1.3 connected to LED. So, what is the situation? So, we have got so we have got the situation like this, that we have got this P3.3. So, this P3.3 is connected to a pulse generator. So, here I have got a pulse generator that can generate this type of pulses, and so falling edge of the pulse will send high to P1.3. So, P1.3 is there. So, this is the P1.3, and there I have got one LED connected. So, here some LED is connected here. So, if I put a 1 at this point, the LED will glow. Okay. So, this program, so we can develop using this interrupt. So, this when this pulse low edge will come, so it will generate an interrupt, and that interrupt will be interrupt service routine will be putting a 1 at this point.